morning, everyone. Thank you very much for joining us today for the 9th annual meeting of the Innovation for Cool Earth Forum, hosted by the Ministry of Economy, Trade and Industry, and New Energy and Industrial Technology Development Organization. For the first time in 3 years, despite the continuing influence of COVID-19, this forum is being held in a hybrid format, both in person and online. And now we would like to start the side event. As a COVID-19 measurement, please always wear your mask and pay attention to general hygiene precautions such as regular hand washing, hand sanitizing, and proper etiquette with coughing and sneezing. If you're not feeling well, please contact the Secretariat for help. In case of emergency, please follow the instructions of the staff. My name is Watanabe Akiko, serving you as an MC for this session. Now, let us begin the side event, Moonshot R&D Program, CO2 Balance, and Outlook of the Moonshot DAQ projects. To start the session, Dr. Yamada Hiroyuki, Director General, Moonshot Research and Development Program Office, Frontier and Moonshot Technology Department, NIDO, will give an opening address. Dr. Yamada, if you please.
Okay. Hello, everyone, wherever you are. Good morning for attendees in Japan. And I'm sorry that it will be late night or very early morning for overseas participants. Thank you very much for joining us today. For ICEF side event, named Moonshot Research and Development Program, named CO2 Balance and Outlook of Moonshot DAQ projects. My name is Yamada Hiroyuki, Director General from Frontier and Moonshot Technology Department of NEDO. And I will act an opening address. We and NEDO promotes the Moonshot Research and Development Program. And as a program, in 2020, we started 6 direct air capture and carbon dioxide utilization projects. That's DAQ project. Last year in ICEF, we introduced our projects and discussed with overseas keynote speakers and about future prospects of direct air capture technologies. Since then, each project is progressed, and their image of the system is being designed. We also recognize that the measurement of carbon dioxide emission through the system, such as life cycle assessment, LCA, is very important. So, NEDO requested project managers to consider CO2 balance of their system with LCA. In this event, each project manager will present their project outline and LCA status. And this year, we invite 2 experts as keynote speaker from overseas. Mr. Gregory Cooney and Dr. Volkasik, who are known as famous researchers of direct air capture, CO2 utilization, and life cycle assessment. And they will present their thought in their keynote speech. And in panel discussion, I expect that the future prospect of a DAQ system and its role will be discussed between keynote speakers and our project managers. Today, I'm very glad to hold this side event in ICEF again, and to present our project progress to the audience. Total of this event will be 2 hours. I hope you can enjoy and you will hear the discussion until the end. Thank you again, please enjoy this event and ICEF. Thank you.
Thank you, Dr. Yamada. Next, Dr. Yamaji Kenji, President Research Institute of Innovative Technology for the Earth, will also give an opening address. Dr. Yamaji, if you please.
Good morning. As introduced, I am Kenji Yamaji, President of Research Institute of Innovative Technology for the Earth, RITE is the abbreviation. But on this occasion, it is more important. I am a program director of Moonshot Goal number 4, and also I am a steering committee member of ICEF. And on this occasion of the opening of NEDO's side event of ICEF2022 on DAC-U project. DAC means direct air capture, but direct capture, CO2 capture from air, we abbreviate as DAC. And with captured carbon dioxide is used, so the abbreviation is DAC-U projects. Okay, so Japanese government started Moonshot type research and development program in 2020. And, okay, let me show the slide. Yes. And, okay, let me first, the Moonshot Goal 4 is a realization of sustainable resource circulation to recover the global environment by 2050. But, okay, left-hand side, that explains the total Moonshot program. The Japanese government started Moonshot type research and development program to develop radical solutions for difficult social change. And so far, government of Japan adopted 9 Moonshot goals. And number 4 goal is among these 9 Moonshot goals. Okay, so the Moonshot goal number 4 is funded and managed by NEDO. Okay, and for the Moonshot goal 4, we adopted 13 projects, including 7 DAC-U projects. As shown in the left-hand side slide, part of the slide, there are 3 parts. One is, of course, direct air capture and utilization. It is shown in blue. And on the upper left-hand side, it's shown in green, is a marine plastic problem. To detoxify the marine plastics in the marine dissolved automatically by inventing various type of switch to start the decomposition of the plastic. And the yellow is nitrous oxide issues. Nitrous oxide is the most has overshooted planetary boundary aspect. So we deal with these 3 areas, and 7 projects are adopted in for DAC-U project, and 3 for marine plastic, and 3 for nitrous oxide problem. Okay, then I rather focus on the DAC-U project. Okay, As already mentioned, so far adopted 13 projects. 7 projects are challenging this direct air capture and utilization. There are various types of capture technologies, membranes, or chemical absorption, or electrochemical type, or mineralization. So probably in the latter part of this session, each project manager explain you their research and development. And we aiming commercialize low-cost, high-efficiency DAC-U technologies. Okay, today we have 2 keynote presentations and panel discussion with some focus on life cycle assessment of DAC-U among keynote presentators and 5 project managers of DAC-U area of Moonshot Goal number 4. I hope this event stimulate your interest in DAC-U projects. Thank you very much.
Thank you, Dr. Yamaji. Now, let us present the introduction video. First, Mr. Murata Jo, Chief Officer, Moonshot Research and Development Program Office, Frontier and Moonshot Technology Department, NEDO.
Thank you very much for joining us today for our session. My name is Murata Jo, Chief Officer of Frontier and Moonshot Technology Department in NEDO. In this part, I will introduce our DAC-U project of Moonshot Research and Development Program and this session. In the Moonshot, NEDO is working on Cool Earth and Green Earth. By 2050, we aim to globally deploy commercial plants and products that will contribute to Cool Earth or Green Earth. In addition, by 2030, Cool Earth aims to develop circulation technology on a pilot scale for reducing greenhouse gases that is also effective in terms of life cycle assessment. Towards this target, we have several DAC-U projects underway. We think that our targets are challenging. We know that in the United States, many companies are working on DAC-related technology development using the US national budget as a source of funding. You can see this includes many early-stage startups. We recognize that many of them are aiming to commercialize DAC and are working to improve the energy efficiency of CO2 recovery. In other words, I think including well-known leading players such as Primark, Carbon Engineering, and Global Thermostat is current situation that are trying to improve the energy efficiency of CO2 recovery by using the national budget. I think the US is characterized by the development of innovative elemental technologies for DAC and the implementation of the demonstration. On the other hand, I think the Moonshot characterized by the development related to system from CO2 capture to conversion that we are working on the DAC-U project. This is today's program. Today, we have invited Dr. Inaba, an LCA expert, as a moderator. We have also invited 2 keynote speakers from the US, which I mentioned earlier. Today, we will have a panel discussion with 2 keynote speakers and 5 project managers regarding the LCA of Moonshot DAC-U system. Please watch till the end. Thank you.
Thank you, Mr. Murata. Next, Dr. Inaba Atsushi, President, Japanese Life Cycle Assessment Facilitation Center.
Good morning, everyone. I am now the president of Japan Life Cycle Assessment Facilitation Center, but I used to be a researcher of coal utilization technology such as coal gasification and coal liquefaction. Since 1993, that is the time ISO started the development of the new standard of life cycle assessment. Since 1993, I have deeply involved in life cycle assessment activities. Today, I would like to introduce the short story of life cycle assessment and then also introduce the purpose of this session. In the history of life cycle assessment, I think there are two waves, and now we are in the third wave. The first wave is around 1997, the time ISO published the first standard of life cycle assessment. At that time, big companies understood what is life cycle assessment, and they used life cycle assessment for business to business. The second wave was carbon footprint of products. CO2 emission of the consumer products sold in the supermarket were calculated and shown to the consumers. And then we are now in the third wave, that is carbon neutrality. This slide shows the concept of life cycle assessment using an example of a refrigerator. Environmental burden such as CO2, SOx, resource consumption of the refrigerator in the life cycle are calculated from cradle to grave. Life cycle assessment of the ISO standard 40040 and 44 has four phases. First is goal and scope, and second is inventory analysis, and third one is impact assessment, and then interpretation. ISO said we can use the life cycle assessment result for so many things. Is the second wave of life cycle assessment. It was carbon footprint of product. This slide shows the first carbon footprint in the world: Walker's potato chips and orange juice of Tesco in UK. After UK, so many countries started the carbon footprint of product. These are the logo marks of carbon footprint of product. Japan, UK, France, Korea, Thailand, and Chinese Taipei. ISO standard of the carbon footprint of product, ISO 40067, was published first in 2013 and it was revised in 2018. Now we are in the third wave. It is carbon neutrality. ISO started the development of a new standard of carbon neutrality in 2020. It is ISO standard 40068, which was proposed by UK. The convener and the secretariat are from UK. I am attending to this activity as an expert from Japan. This new standard is currently in the stage of committee draft. It will be published in the next year, 2023. In the current draft, carbon neutrality means in the final stage, residual emissions equal to removal enhancement plus buying the carbon credit. Toward the final stage, on the transition stage, we have to consider the change of the company portfolio and reduce the GHG and then offsetting. I would like to focus here removal enhancement. I think that include DAC, direct air capture, DAC-U, CCS, CCSU, BEX, and so on. I would like to discuss how much GHG we can reduce by our project in this session. I would like to show you this slide again, because in order to calculate CO2 or GHG emissions, first of all, we fix the system boundary to calculate GHGs. And then we have to collect the foreground data and find the background data. Today, as I mentioned before, I would like to consider how much GHGs we can reduce by our project in this session. As the start point of the development of new technology, we would like to establish the methodology to calculate CO2 or GHG emissions. We have to consider system boundary, secondary data, and so on. I would like to discuss these kind of things after the presentation of our guest keynote speakers and project leaders. In the panel discussion, I would like to discuss with them. Thank you for your attention. I would like to see you again in the panel discussion. Thank you.
Thank you, Dr. Inaba. Next, we would like to introduce the presentation video from the panelists of this session. First of all, Mr. Gregory Cooney, Senior Engineer, Office of Carbon Management, U.S. Department of Energy. His area of expertise is life cycle analysis, assessment, carbon capture, utilization, and storage, carbon footprinting, accounting.
Hi everyone, my name is Greg Cooney and I am part of the U.S. Department of Energy and work in the Office of Fossil Energy and Carbon Management. And today I'm going to talk about applications of life cycle analysis to direct air capture and carbon dioxide utilization. So first, I think it's important to sort of motivate why we think LCA is necessary when evaluating carbon dioxide removal technologies. So we know within the context of these technologies, there's quite a bit of focus on defining the sorts of measurement and verification systems for the amount of carbon dioxide that's actually removed and permanently stored. But we also know that there's a variety of potential impacts, sort of offsetting impacts that occur both upstream and downstream of these activities. And those include things like the material and chemical and energy inputs, as well as any of the sort of downstream mitigation activities, transport, permanent storage as an example, as well as conversion into other potential products. And so LCA as a framework is quite helpful in thinking about the implications of the entire value chain, and in the case of CDR, can help us understand where there might be sort of offsetting impacts and positive emissions along the supply chain. And so just sort of two specific examples as they relate to direct air capture. The figure on the left is from a recent publication that evaluated the carbon footprint of captured CO2 from direct air capture. This particular figure looks at that value as a function of the carbon intensity of the electricity mix. And so what you can see is, short of an LCA view, all sort of DAC in this case would be treated equally, but what's shown here is the carbon intensity of the grid depending on where you're located in the world. The timing of the deployment sort of matters significantly in terms of the ultimate benefit in terms of net removal. The figure on the right is from a recent study by NETL, and sort of depicts the same thing in a slightly different way. And so the point here is for two different designs of direct air capture, there are coarse removals, but then there are sort of these positive emissions that occur to support the requirements of the process itself. And so I think these are good illustrations of why we would want to apply LCA in the context of DAC specifically. More broadly, LCA is quite useful, I think, in helping us think about carbon dioxide removal approaches, in coming up with an assessment of the net emissions associated with each potential approach, and then sort of having a real evaluation of any potential trade-offs that might occur across a range of potential environmental impacts, even though the focus is largely on greenhouse gas mitigation. I think when coupling direct air capture to utilization, it's important to sort of understand that inherently utilization doesn't imply a benefit in terms of climate, but it does beg the evaluation in a comparative sense. And so the LCA will help identify where there are potential issues or potential opportunities to link these technologies in a way that's sort of beneficial on net compared to existing technologies. And ultimately we want to do the LCA to make sure that we're ending up with a net benefit. It may not end up with a system that's carbon negative or carbon neutral, but we want to make sure that the systems that we're evaluating are in fact carbon reducing. One of the, I think, challenges of applying to LCA, or applying LCA to carbon dioxide utilization systems, is the fact that the system encompasses both the source of the CO2 as well as the sink. And so those are often in completely different sectors within an economy. And so it just necessarily increases the complexity of the system because of the wide variety of potential sources and wide variety of potential sinks. The benefit of having this combined system is that we can define a comparison system that provides the same function to society, which ultimately allows us to do a consistent analysis with the goal of having a system that is comparable, so that we can help provide input for robust decision making. There certainly are existing standards in ISO that help define the requirements for LCA and the practices for LCA, but there are a variety of subjective elements that are left to the practitioner to determine for each particular study, and depending ultimately on the goal and purpose of that study. And I think this is especially true in the sort of the coupling of direct air capture and utilization. It's critical in terms of developing a system that can be compared, to have clarity and consistency in the functional unit of the system. And I think that also stems from having a clear understanding of what the system boundary encompasses. I think the other area that we've seen some potential confusion and misunderstanding is in the context of accounting for negative emissions, broadly in LCA and sort of the application in these systems in particular. And there's a couple of other challenges that are noted here, but I think these are opportunities to help inform an LCA that can be useful when evaluating these coupled systems. And one of the things that we've done in the U.S. Department of Energy is develop a set of best practices for evaluating direct air capture, ultimately with the sort of overarching goal of having robust LCA that are consistent. We understand where there's uncertainty and sensitivity in the assessment. We look at potential trade-offs, and really we sort of leverage the best practices from the LCA community. So I'm just going to talk through a couple of the recommendations in that document, and it's sort of what we learned in sort of approaching this problem. And the first is around the functional unit. We know that this is sort of the critical element in the goal and scope phase of a life cycle assessment. And when it pertains to DAC, we've seen a variety of different functional units used in the literature, and ultimately they sort of result in studies that aren't directly comparable because they don't yield a consistent function. And so in our best practices, we think about what the potential suite of functional units could be for this sort of system. In the context of a sort of notional example, show how the choice of the functional unit can impact the results and the interpretation of those results going forward. And so even though these all look quite similar, there are sort of nuances that change what's included or excluded from the function itself. And just as shown here, there are sort of real impacts associated with the choice of specificity to define the functional unit. On a system boundary side, we know there's lots of different ways of evaluating a system, whether it's sort of gate to gate, thinking just about the direct air capture process itself, extending that boundary upstream to look at the sources of energy and raw materials used in that process, or going downstream and looking at the fate of CO2. And so, I think it's important to be clear about what the boundary of analysis is, and I think obviously a coupling of DAC with utilization necessitates a wider boundary on a cradle-to-grave basis. And so the best practices that we have advocated for in those decisions look at capture of atmospheric CO2, a cradle-to-grave boundary, and then a boundary that encompasses the downstream fate of the captured CO2, in this case, the conversion of that CO2. One of the other elements that we tried to address in the best practices was how the accounting of negative emissions should be thought of in the context of LCA. And so we sort of framed it as these sort of two situations in LCA where negative values can arise. The first is when there's a removal of an emission species from a particular environmental compartment, such as atmospheric removal from the cultivation of biomass or from engineered approaches. The second approach is, or the second situation is when there are avoided emissions. And this really occurs when a system has multiple products and the practitioner has chosen to manage those products using a substitution or avoided burden approach. And that introduces a negative value as well. What we're trying to be clear about is the interpretation of those negative values is quite different. One is a removal and one is an avoidance. And one scales with the functional unit, and the other may or may not necessarily scale with the functional unit. So in our sort of example system here, we crafted a scenario in which we look at a system with a co-product, and we show how the interpretation of the results could be quite different. And so what we ultimately are proposing is that avoided emissions and atmospheric removals should be reported separately in these types of systems, so that there is no ambiguity in the understanding of what those values mean. And oftentimes they're clumped together as a single result. In the context of utilization, I wanted to point to a toolkit that exists, developed with the Department of Energy's National Energy Technology Lab for evaluating carbon utilization projects within the program portfolio. And really the toolkit was developed to improve the clarity and specificity of the guidance so that we could have accurate LCAs that could be sort of compared apples to apples by the program, and at the same time minimize the effort that's required to complete the LCAs as part of the project that's developed. And you know, as part of the development of this toolkit, our goal is to participate in a wider global effort to harmonize this guidance, which is demonstrated on this slide. So there is an international working group that is convening to look at the methods of LCA as applied to utilization systems. And there have been a variety of publications that have resulted as a result of that effort. And so the final slide I want to leave with today is sort of thinking about how the questions that are posed by the LCA sort of define the approach that should be taken when crafting the LCA. And so, you know, I think broadly there are, you know, these two buckets of LCA, attributional and consequential. And I think this figure is helpful in sort of beginning to sort of understand the differences between those two types of analyses. I think it's important for the evaluation of these coupled systems to determine which bucket the question should lead the practitioner towards. I think there are attributional and consequential questions related to these systems, and I think it's important to understand which approach is relevant and also understand the limitations of extending a result from one approach to answer a question that might be better aligned with another approach. So with that, I thank you for your time and attention, and appreciate the opportunity to present to you all, and would like to point you to the resources that I mentioned during the discussion today. And I look forward to the rest of the conversation in the session. So, thank you very much.
Thank you, Mr. Cooney. Next, Professor Wolfgang Sick, Professor, Department of Mechanical Engineering, University of Michigan. His area of expertise is CO2 utilization, life cycle assessments, techno-economic assessments, laser diagnostics, the internal combustion engine.
Welcome, and delighted to be part of this exciting session today. My name is Volker Sick. I'm the director of the Global CO2 Initiative at the University of Michigan. I'm excited to share with you today information and ideas about how CO2 can be a solution to the CO2 problem. So I will provide you the answer to this question here that I'm posing in this forum. And I'd like to start by first describing why we have the formidable task at hand and how we can think about challenging but really feasible solutions. So let's first look at the magnitude of CO2 that we have to deal with. Over the past few centuries, we have, through the use of fossil carbon sources, added more than 1 trillion tons of CO2 to the atmosphere and water. And these so-called legacy emissions are some of the most important elements in this whole CO2 conversation. Of course, as we continue to develop technologies and means to decarbonize what we can decarbonize, the fact that CO2 is such a non-reactive molecule means that it stays in the atmosphere, and in order for us to stabilize the climate, we have to remove some of that CO2. Now, that has to happen really fast and at a very large scale. So for a moment, let's assume we can do that. We also know that we cannot remove all CO2 emitting processes from our everyday lives. Some of the emissions will stay with us and continue to add CO2 to the atmosphere. So we have to think about, what do we do with that CO2? How can we address that so that over time we do not really build up another large amount of legacy emissions? So that's really critically important to keep in mind. But back to these legacy emissions that we deal with already, we need to remove a lot of CO2 in a record short time. And for that, we need to build up a huge industry. When we are done with removing the CO2, what happens to that industry? We don't need as many facilities to take care of the inevitable emissions. So this is an economically challenging problem to address and plan carefully, how we build up and phase out a significant number of installations. So how can we sort of think about dealing with all of that? Well, you know that in the context of carbon management, carbon capture is only the first step. Once we have the CO2 isolated from water or the air or emissions from industrial processes, we then are faced with making a decision what to do with that CO2. We can store it underground in so-called CCS processes, or we can turn our attention to CCU, or carbon capture and utilization. And there are some pronounced differences in how these two different categories of dealing with CO2 do work, but common to anything we do with carbon capture and utilization, we are ending up with a product. Whereas carbon capture and storage typically produces a service that is removing the CO2 and keeping it away safe. So let's stick with utilization for the moment and look at it a bit more closely. If we look at how we make products, we have defined tracks for materials that are distinguished by how long these products live. And we call track 1 materials those materials that remove CO2 for more than 100 years, many of them actually, as I will show you, for what could be considered permanent. In contrast to that, track 2 materials remove CO2 for less than 100 years. Many of them actually release CO2 through their consumption in far shorter time scales. For example, if we produce fuels or chemicals that decompose. So in a sense, track 1 and track 2 allow us to merge, overlap carbon capture and storage and carbon capture and utilization, because track 1 materials functionally provide the same performance as carbon capture and storage. The CO2 is removed. So making these products essentially is equal to a CDR, or carbon dioxide removal process. And therefore, one could talk about CO2 removal actually as something like a surface CCS, whereas circular carbon economy and fossil-free carbon products are enabled by the production and use of track-2 materials, because we continue to have access to essential carbon-based products without the need to deploy fossil carbon resources. Let's look closely what kind of products we can actually make. In a study that we have put together some years ago that you can obtain from our website as a free download, we have identified product categories that begin with construction materials, go to fuels, chemicals, so-called engineered materials that include carbon fiber, carbon nanotubes, etc. But also polymers and agricultural and food products all can be made with CO2. And in some of them, there is clearly just a swap, a replacement of the carbon source from fossil sources to CO2 as this raw material. Whereas for some of the food products, it's clearly a new pathway to use CO2, for example, to make proteins in a technological process. Of course, nature does this every day in plants. But what's definitely a very new endeavor and a very large opportunity for climate-relevant action is the use of carbon dioxide to make construction materials. In particular, concrete and aggregates provide opportunities that are very large in terms of the amount of CO2 that can be consumed, as well as the revenue that could be generated. And that's another really key recognition, that by producing products that can be sold, we can actually generate income and thereby help pay for the CO2 removal process. So what you see here is the augmentation of this earlier report with our new classification with tracks. For example, construction materials clearly will fall into the category of track 1 materials. Concrete, aggregates, rocks essentially are long-lived and thereby fulfill the definition of track 1 materials that live for more than 100 years. Whereas fuels very clearly are a key example for a track 2 material. We make it, we use it, the CO2 gets re-emitted. And then polymers are sort of in between, maybe some engineered materials too. And that depending on the nature of these materials, they could be long-lived. In fact, many polymers do, which is why, amongst other reasons, we have so many problems with plastics in the environment. And therefore, there's a set of opportunities by cleverly tailoring the lifetime of some of these products. So I want to share with you some very recent results from new work that we have recently released. Again, material can be obtained at no cost from the Global CO2 Initiative's website. What I'm sharing with you here is a very busy plot of how the opportunities for aggregate production with CO2 develops over time. So let's focus first on the amount of CO2 that we could use every year to produce aggregates. And we start our projection in 2025 and then look forward in 5-year increments all the way to 2050. And the bars here show 3 scenarios. We look at a baseline scenario that does not do anything specific to provide strong incentives to pursue CO2 utilization. Whereas in an optimistic case, and definitely in a best case scenario, there are mechanisms, largely financial mechanisms in place that support the production of aggregates with CO2. So there is clearly, let's look at it here in 2050, a significant impact of such activities. But even in a baseline case scenario, if we look at 2050, nearly 4 gigatons of CO2 every year could be utilized to make aggregates. Now, what you see here too is a very large error bar. That error bar indicates the range of materials that can be made. On the upper end, if we produce calcium carbonate or limestone-like materials, that is the maximum amount of CO2 that we can think of permanently putting away, with 44% of that material being based on CO2. Whereas other minerals might take far less CO2 per ton of material produced, and hence the opportunity is lower. In that particular case, the range goes from about 1 gigaton a year to about 5. So very significant. It depends really on what we produce, and that is certainly a function of where we actually source materials. But the key is also these gigaton levels of CO2 use are achieved with already very low levels of market penetrations. That's shown here by these diamonds. Right? That is the range of market penetration that we could see. Right? So there's huge potential, absolutely huge potential for CO2 utilization with aggregate production. But how do we decide which technologies are best? Right? It's absolutely important to understand that there are some CO2 uses that can become carbon negative. Many can become carbon neutral, which is still a win, if and only if we have zero carbon energy for all of these processes. Otherwise, we really, especially for track 1 materials, need to make sure that we fully understand the full CO2 life cycle balance. And of course, none of these things will happen if the economy doesn't work out, right? So assessments are critical to simultaneously study the economics and the environmental impact. Thus, a multitude of other factors beyond these. For example, are there alternative technologies that compete, that have nothing to do with CO2? So these assessments are at the core of success here. And we therefore can note that we've seen that carbon capture utilization and storage can be complementary. With track 1 materials, those that are lived for more than 100 years, they actually have something in common. We also keep in mind that carbon capture and utilization creates revenue from products, and those revenues can help offset the cost of capturing the carbon. And then lastly, I have introduced to you track 1 products and track 2 product classifications as a way to easily understand the climate benefit of different ways of CCU. So I thank you for your attention and look very much forward to the discussion. Thank you so much.
Thank you, Professor Sik. Next, Professor Kodama Akio, Professor, Institute for Frontier Science Initiative, Kanazawa University. Professor Kodama has contributed us with the video but will not participate in the discussion.
Good morning, everyone. I'm Akio Kodama, manager of this project. This is a collaboration work of Kanata University and Research Institute of Innovative Technology for the Earth Right. This is the outline of our project. The final target is this carbon recycling system. The key technologies are a low-temperature driven DAC and a membrane reactor that converts CO2 into liquid fuel. In this regard, RIGHT is trying to develop a new amine that can be easily regenerated by low-temperature heat. In the final phase of this project, we plan to conduct a life cycle assessment and economic evaluation of this entire system. But today, we will focus on the unit that combines the DAC and CO2 conversion process. The proposed DAC-U is a combination of steam regenerative DAC and FT synthesis process. The main input of thermal energy and electricity are shown. Also shown in the general flow of thermal energy. In the FT synthesis process, electricity is consumed mainly for compressing the feed gas and controlling the reactor temperature. Here, energy consumption for hydrogen production is not considered. On the other hand, the reaction heat released from the FT reactor can be used to operate the DAC. If this amount of reaction heat is not sufficient for the DAC, low temperature heat or solar heat is supplied to the system. Heat pumps might be an attractive heat source because of their flexibility. This is another type of DAC-U we propose, which combines a two-stage DAC with FT synthesis process. In the first stage of this hybrid DAC, atmospheric CO2 is once concentrated in this honeycomb rotary adsorber and then highly concentrated in the second stage. By reducing the amount of process air, the second stage can be made smaller. We believe this reduces the energy consumption of the entire system. Taking into account available energy sources, the second stage can be equipped with a variety of conventional or developing enrichment processes. This allows for greater flexibility in system configuration. A life cycle assessment will reveal the optimal DAC configuration and connection conditions. However, inventory data for conventional enrichment processes as well as developing processes is also needed. Finally, the issues and questions for applying LCA are listed here. In special, I ask about the environmental impact of thermal energy use. Our proposed DAC is thermally driven and can use low temperature waste heat or solar heat. I think CO2 emissions during waste heat utilization should be zero. At least, its temperature level should be considered in the evaluation. But there seem to be no established rules. In this regard, exergy may be a more accurate indicator for heat utilization than enthalpy. That is all. Thank you for your attention.
Thank you, Professor Kodama. Next, Professor Sugiyama Masakazu, the Director and Professor at Research Center for Advanced Science and Technology, the University of Tokyo.
Hello, I'm Sugiyama, University of Tokyo. I'd like to introduce our system of the CO2 capture utilization and the CO2 emission out of the process. Our process aims at the collection of the CO2 from our atmosphere using physical adsorption and desorption process. The concentrated CO2 is further enriched and purified by our novel electrochemical reactor. The outlet, almost 100% concentrated CO2, is then introduced to electrochemical reactor, which reduces the CO2 into ethylene, which serves for a building block for variety of the useful chemical feedstocks. For the analysis of the CO2 emission, we here focus on the CO2 electrochemical reduction process and set the boundary as this. Inside of this boundary, here exists our major development target, electrochemical reduction of the CO2. Here, the cathode includes the unreacted CO2, which is split through the electrochemical process and recycled to the inlet. And CO2 crossovers to the anode side, and this CO2 is again split by the electrochemical process and recycled to the inlet. And also we have a cryogenic separation of the product ethylene, and out of this boundary, only ethylene product is emitted. For these separation processes, we assume the typical energy footprint, and also for our development target, the electrochemical reduction process, we assume the process performances, which is set as the project target. And the CO2 footprint in electricity is very important because this process is very electricity intensive. And we here assume rather small value of the CO2 footprint, assuming the photovoltaic electricity. This is the emitted CO2 out of the process of the CO2 reduction. This portion corresponds to the CO2 fixed in the form of ethylene, while the most of the positive CO2 emission comes from the electrochemical reduction process. So, as this sensitivity analysis shows, the largest sensitivity for the CO2 emission exists in the electrochemical reduction process, such as the Faraday efficiency and cell operation voltage. So, improvement of these performances in our project is very important to realize the CO2 negative process. The next target of our analysis is to include the CO2 adsorption and desorption process and the electrochemical enrichment process so that we can more comprehensively analyze the CO2 emission out of our system. Thank you for your attention.
Thank you, Professor Sugiyama. Next, Professor Noguchi Takafumi, Professor, Department of Architecture, Graduate School of Engineering, the University of Tokyo.
My name is Takafumi Noguchi. I would like to make a presentation on C4S project. Limestone was formed in the ocean and the mountains through carbon dioxide absorption in ancient times. A large amount of carbon dioxide is emitted through limestone calcination during cement production. Cement is used to make concrete structures. A cumulative amount of carbon dioxide from limestone calcination is 55 billion tons. On the other hand, calcium is left in the concrete and dispersed throughout the world. In C4S project, carbon dioxide and calcium will be combined again to form calcium carbonate concrete, CCC. How can we make CCC? Concrete waste is carbonated first. Then, the particles of concrete waste are put in the container and powdered in the cold water. Air is injected in the water to produce calcium bicarbonate solution. Then, the solution is given between the particles and heat is applied for the precipitation of calcium carbonate crystal as a binder. CCC can be carbon negative, produced using local ubiquitous resources, and become completely recyclable. If 50% of concrete structures will be constructed with CCC in 2050, captured carbon dioxide will become 1 billion tons per year in the world. Carbon dioxide emission from C4S is compared with conventional concrete. Conventional precast concrete is produced by using new cement and aggregate and steam curing. After the structure is enriched, concrete waste is crushed to become roadbed materials. On the other hand, in C4S, concrete waste is crushed and used as raw material for CCC. The difference between the two is the blue and green part. By comparing these, we can evaluate carbon dioxide reduction in C4S. At present, The strength of CCC slightly exceeds the legal requirement. Further enhancement is needed in strength and size. The higher the particle filling rate and the greater the amount of calcium carbonate precipitation, the greater the strength. Therefore, we are aiming to incorporate pressure and carbon dioxide curing. Currently, CCC in the laboratory emits a lot of CO2. In the future, we will improve energy efficiency and make it carbon negative. The more CCC produced, the more carbon dioxide captured. Thank you very much for your kind attention.
Thank you, Professor Noguchi. Next, Professor Norinaga Koyo, Professor, Institute of Innovation for Future Society, Nagoya University.
My name is Koyo Norinaga, Nagoya University. I am working on the direct air capture that utilizes liquefied natural gas coldness. We call this as cryoDAC. CryoDAC is basically a chemical absorption process. We first capture CO2 from the air with liquid. Then this liquid is transferred to this dissolver. Then in this sublimation tank, the latent heat of LNG is exchanged with CO2 to convert CO2 gas into solid, dry ice. As a consequence, the pressure of the dissolver connected to this tank is reduced, and the CO2 is released from the liquid and collected here. The chemical absorption is usually operated by temperature swing. On the other hand, our process is operated by cryogenic pumping, namely pressure swing amine process, while keeping the dissolver temperature as low as possible, and we can hope to minimize the thermal energy input. We are collaborating with both university and industries. One of the most possible scenarios involving this cryoDAC is to convert the captured CO2 into methane by the methanation process with green hydrogen. We call this synthetic methane as carbon-neutral methane that we can expect to be accepted in the future carbon-neutral society. The benefit we can expect by this carbon-neutral methane can be that we can use the existing town gas infrastructure and can minimize the additional social cost. The life cycle assessment is important in making the cryoDAC to be a real option. Here we can see the boundaries. We consider 4 boundaries, including 4 carbon circulation systems. That is the largest boundary we set, and the smallest sub-boundary is DAC only. This is a simple example of the LCA result or DAC only case. One of the advantages of the cryoDAC is that we need thermal energy input lower than other DAC technologies. Here we can see the life cycle CO2 emission of cryoDAC. We consider the CO2 emission from capital goods based on the equipment list suggested by the process simulation and the database provided by National Institute, and we can say this makes a small sense. So if we look at their operation, even if we use current CO2 emission factor in 2020, we can already have enough CO2 removal. And if we think 2030 case, the lower CO2 emission factor can make more CO2 net removal. And in 2040, we will be able to make much more CO2 removal. Our future challenge for the life cycle assessment is to extend the boundaries to analyze full carbon recycling system. Thanks for the listening.
Thank you, Professor Norinaga. Next, Professor Fukushima Yasuhiro, Department of Frontier Science for Advanced Environment, Tohoku University.
Ladies and gentlemen, I will briefly describe our Moonshot project on chemicals production from atmospheric CO2. I am Yasuhiro Fukushima from Tohoku University, Japan. Here, I present the combined carbon capture and conversion, or QuadC, to produce organic urea and carbamate esters, characterized by more energy-saving and safer production. This is an example process system with a QuadC module realized by a selective CO2 permeating membrane at its core. This membrane avoids the absorbent amine to transport to the other side of the membrane, which becomes a loss otherwise. So far, a membrane with excellent selectivity with a reasonable permeating rate has been developed for our project. The intermediate, called carbamic acid, dissolved at a near saturation concentration in the amine, is converted to the chemical product, here an organic urea, in a catalytic converter located in this post-QuadC module. In typical carbon capture and utilization system, the carbamic acid is heated to provide a pure CO2 gas stream for the subsequent reaction. We made this energy consumption for heating unnecessary. We have already confirmed that two different combinations of modules with the same principle can provide the model product, which is ethylene urea. Our project provides various modules, process design schemes demonstrated by 4 chemicals that we have chosen, and LCA models that can be adapted to various cases to assist the process innovations for production of a variety of chemicals from atmospheric CO2. In general, the CO2 can be used for production of basic chemicals and intermediate or final chemicals. The latter is our character approach, which can actually make it limited in market size for the respective chemicals. We tackle this by implementing mechanisms to diffuse the innovation to many chemicals. From a life cycle point of view, with the basic chemicals production, the amount of CO2 captured can be relatively large compared to the associated cradle-to-gate GHG emission. For downstream chemicals, on the other hand, the GHG emission per kilogram of product becomes both greater and more dependent on the background emissions in relative to the carbon captured for its production. So here's our system boundary, and here's the part of results. Most of the emissions were from consumption of reactants. More experiments are ongoing to make these numbers more fact-basis at a more reasonable production scale. Being at the early stage of process development, we still have lots of degrees of freedom in the design. In our project, LCA is used in a deductive way to acquire insights useful in process design. For example, this figure suggests that the CO2 recovery ratio do not need to come close to the current known DAC system. This kind of insight provided from LCA is utilized for design of QuadC modules, such as membrane module I have already introduced, or an absorption-based QuadC module that integrates capture with conversion. That's all for now. Thanks for your attention.
Thank you, Professor Fukushima. Next, Professor Fujikawa Shigenori, Distinguished Professor, International Institute for Carbon Neutral Energy Research, Kyushu University.
Hello everyone, my name is Shigenori Fujikawa. I'm a project manager of one of the Moonshot project entitled The Development of Global CO2 Recycling Technology Toward Beyond Zero Emission. We have recently developed the new CO2 separation membrane with the ultra-fast CO2 permeance. The reason why this membrane has the ultra-fast CO2 permeance is the thickness is only 34 nanometer, which is 300 times thinner than the food wrap. Actually, this is thinner than the COVID-19 virus. And this nanomembrane has a pretty high CO2 permeance. Actually, this is world high and overwhelming higher permeability, 20 or 30 times higher than the previous reported case. Based on this achievement, we would like to develop the new direct air capture system. After CO2 capture by nanomembrane, we have to also consider the CO2 conversion after the membrane-based direct air capture system. We are now considering 2 methods to convert the CO2. One is the electrochemical conversion, the second is the thermochemical conversion. Actually, in electrochemical conversion, it doesn't need any hydrogen supply because the water is a hydrogen source. So based on working with Professor Miho Yamauchi, who is a Kyushu University professor in Japan, and also Professor Paul Kenneth, University of Illinois Urbana-Champaign, they are developing the new electrochemical system for the CO2 capture CO2. And in second, Professor Shim is also working on the thermochemical conversion by using hydrogen. He developed a very unique catalyst for the methanation and some other CO2 value-added product, as shown here. Then we would like to combine system as shown here. We named as direct air capture and utilization system. Firstly, we separate the CO2 from the air, as shown here, and then capture CO2 directly introduced into the CO2 conversion unit, as shown here. Then, finally, we could obtain such kind of value-added carbon resources. This is all we call this system is direct air capture and utilization system. And our final aim is to deploy such kind of small unit into the city area as shown here. And then actually, so because downtown area is a very CO2 emittive area, that is why such kind of small unit can be installed in somewhere in the city area. And then after CO2 capture and conversion, we can circulate converted CO2 in the city area. We would like to promote a local production and local consumption carbon recycling society. And of course, LCA, life cycle assessment is a very important issue. Of course, in our system also we are considering life cycle analysis based on the cradle to grave scope. And also we compared among the different conversion approach, thermal conversion and electrochemical conversion are conducted. And also hotspot of the CO2 are identified and feedback is provided to development unit leader to reflect the result to the technology and development. And of course, we have something like a target and future issue, especially for the research and development LCA. Of course, the construction of the LCA inventory data is very important part, not only for the global warming potential evaluation, but also the basis of the socio-economic impact assessment. And we must be done iterative in accordance with the development process. We have a strong close communication with the researchers, scientific researchers, and LCA analysts. And also we are building the model that takes EOL into the account. We need more reference data to consider the EOL. We'd like to learn how other dark technology consider EOL. That is our current. All right, then we'd like to build new technology, especially for ubiquitous carbon capture by using the membrane technology. Thank you very much for your kind attention.
Thank you for all the presenters. Now, we would like to move on to the panel discussion. Panelists for this session, please join us on stage. If you have any questions, please submit your question in English from the live Q&A under the live stream platform. However, please note that all questions may not be answered during the session. Now, I would like to ask Dr. Inaba to moderate the session. Dr. Inaba, if you please.
Okay, thank you very much for your introduction. So my name is Atsushi Inaba. I am a sub-program director. I am in charge of the DACU, 6 DACU project. And I made a presentation in this, beginning of this session, but there was some little, mistake. However, I hope you can understand, my introduction of the life cycle assessment. And today, I asked I invited 2 keynote speakers and 6 program manager, and I asked them to make a presentation about the life cycle assessment, mainly the methodology of the life cycle assessment of their project. So that, I would like to manage this, panel discussion. That is a discussion about the methodology of the life cycle assessment. That is our main target of this panel discussion. And I would like to divide this panel discussion into the two parts. One is a Q&A, because our 6 presentation is very much short, so that keynote speakers have some question and comment. So I would like to take such kind of the question and comment from the keynote speakers. That is the first part. And the second part is I would like to discuss about the relationship between the CCS and CCU, or DAC-U or DAC-S. So that is, I understand that is the main target of the presentation of 2 keynote speakers, DAC-S and DAC-U. So I would like to discuss the relationship or relationship for CCU and CCS. That is the second part. So let me start the first part. That is a question and comment from the keynote speakers. Hello. Hello, Kuni-san and Sik-san. How are you? I would like to have your voice.
Thank you. It's a pleasure to be here, and I very much appreciated the overview presentations of all 6 projects. I think these are very ambitious, very important and advanced studies. And I very much liked that all of the assessments show how they are used to make the technologies better, to understand what we heard in the last talk as hotspots. Because I think the power of life cycle assessment is that we can learn from it while we do the research. We should never wait until we have the technology ready to be deployed and then do a life cycle assessment and hope it's good.
Okay.
And I think that came through very much so. I do, though, would like to hear maybe some thoughts about the available energy. There was a talk about the e-fuels and other chemicals. They all rely on green hydrogen.
Okay.
All the projects need very large amount of electricity. Where does it come from? What's the timeline for that?
Okay, thank you. And please. That is a Kuni-san? Okay.
Yes. I echo Volker's comments. I was quite pleased to see and hear about lifecycle assessment being deployed at early stage, and I think several of the speakers noted there's opportunity for change based on the outcomes of the LCA, and I think that's something that we're very much interested in doing within the Department of Energy, where we're trying to ingrain the life cycle thinking very early on in the technology development cycle. So very pleased to see that, and I think it's really robust work that's being done in support of the technologies that y'all are developing. I would echo the same question that Volker had. That was the same one that came to mind for me, and maybe more broadly, just sort of interested in any particular challenges that any of the researchers have had in the context of developing LCA specific to these projects. Volker and I are both involved in efforts to develop guidance on methods for LCA applied to utilization in general, and so I think that sort of feedback would be very useful for us as well.
Okay.
So, thank you.
Yeah. Okay. Thank you. Today I would like to call you Kuni-san and Sik-san, without the Mr. and Doctor and Professor. Is that okay? Thank you. And if you have any, if you need any more information about our 6th project, please give us your question and your comment. Kuni-san, do you have any question and comment to our, particular project?
No, I don't know that I have specific questions other than the sort of the broad ones that Volker and I both mentioned about availability of low carbon energy and hydrogen and sort of, how that's being considered more broadly. It's something we're certainly thinking about within the U.S. as well. We've got all these projects to sort of deploy large-scale capture and utilization and direct air capture, and so yeah, just curious how you all are thinking about that in the context of these studies and sort of thinking about the potential operating envelope for how they might deploy.
Okay. Is there any project you are very much interested in our 6th project?
I mean, I think they're all quite interesting. I don't know that I could single one out in particular, but yeah, I guess just more interested in sort of general feedback on those questions.
Okay, so the 6th, do you have any project you are very much interested in?
Yeah, I actually would like to ask some questions. Perhaps starting with Fuchikawa-san's work on decentralized direct air capture. I mean, I had the pleasure to visit Japan a number of times, and I'm acutely aware that the center is all mountains, and on the periphery you grow food and have houses. So there is not a lot of space to install large installations for direct air capture. And are the devices that you have shown sort of in response to that, to sort of utilize the little space that is available, or is there a technology advantage to be decentralized?
Okay, thank you. Fujikawa-san, that the question is a very much separate process or something, right? So integrated, not integrated, that is, yeah.
Okay.
Do you have any comment or any, answer, please?
Okay. I have a lot of reason to develop the decentralized system because, of course, atmosphere is anywhere. That is why I would like to capture CO2 anywhere. That is our first and most priority ambitious. And second is based to achieve such kind of purpose, we are trying to utilize a membrane because membrane acts as a kind of air filter. That is why we can install anywhere. This is the second reason. Third reason, so this is kind of technical reason. Of course, membrane separation needs some rather higher, relatively higher CO2 concentration, especially downtown area has rather relatively high CO2 concentration. For example, say in the office room or some, subway, something like that has relatively high, around 1,000 ppm or more than 1,000 ppm. In such case, such kind of rather relatively high CO2 concentration is very effective to reduce the membrane separation energy cost. And also, this is very kind of ambitious. So of course, we have to consider the scenario after CO2 capture. In such case, in the city area, so there is many kind of say gas pipeline system. So once we capture CO2 from the air and then convert, for example, methane, we can utilize such kind of gas pipeline to circulate such kind of value-added compound. That is why such kind of decentralized system has many flexibility and also scalability. Scalability means kind of say photovoltaic system. So if you need a small amount of the system, okay, we provide a small unit. And also if you need a more large scale, you just combine as much as you want. That is kind of our reason why we like to develop the decentralized system. Thank you.
Yeah. Okay, thank you very much. However, usually, we think that, what do you think? Integrated system is very much cost effective.
Yes, right.
So, Kuni-san, what do you think about such kind of the separate system, not the integrated system?
Yeah, no, I mean, I think that's an interesting question. I mean, especially from, not only from a cost perspective, but I also wonder from an environmental impact perspective, if there's also sort of economies of scale. But yeah, I don't know the answer to that. I think that would be an interesting question to potentially ask of that sort of approach. I guess one other question that I did have is you know, the focus has largely been on greenhouse gas emissions, whereas you know, we know that LCA is a more holistic framework that can assess a variety of impacts, and so I'm curious if any of the researchers are evaluating impacts beyond climate impacts, and if they're seeing anything interesting, seeing any potential trade-offs for the technologies of interest.
Okay, that the question is a trade-off of the environmental issues or other issues. So, do you have any any comment to panel? I would like to ask to the panelists.
Thank you for the question. I'm Fukushima from Tohoku University, and as mentioned in my video presentation, our process has an advantage in replacing a relatively dangerous chemical called phosgen, which is really toxic, and we need really careful treatment on its handling. And we can replace that with CO2. So we expect that we would have improved safety in the production of carbonyl-based chemicals. So we would like to quantify this safety aspect, which is not so easy to incorporate directly in life cycle assessment. It's perhaps more into the risk assessment rather than life cycle assessment. And also in our project, we have some, of course, we recycle the unreacted chemical reactants in our process. But within this recycling process, we do have to purge some of the recycle flow in order to avoid the accumulation of impurities. And that comes with water treatment or gas treatment. So we are looking at those water-related impacts or gas-related impacts other than CO2 in our life cycle assessment. But we haven't shown that in our presentation.
Okay, thank you very much. Life cycle assessment is usually take us some, other, so many the environmental impact, including the water and, something. So next is, Norinaga-san. Norinaga-san, do you have any? Sorry.
Sorry, I'm Sugiyama. I want to interrupt.
Okay, please.
Can you allow me?
Sugiyama-san is online. Yeah, please.
Yes. Sorry for the participating online, but I would like to jump into the discussion of whether a decentralized system is effective for the installation in Japan. And my answer is probably partly effective, because as the Sixten has addressed, Japan has a quite severe restriction of the land area. So the integrated and large-scale DAC system is not easy to be implemented, in my opinion. So likely to the Fujikawa Sensei's project, my project is also aiming at the collection of the CO2 from urban sites like the buildings and skyscrapers at the conference site. So I do agree that we could provide one effective option of decentralized CO2 capture and utilization process. But we need to also think about another aspect, which is the supply of the renewable energy. Because any of the DAC, especially vacuum system, as I have stated, is very electricity intensive. So how to secure renewable electricity, or in the case of some chemical system, how to secure green hydrogen is very important to make that kind of decentralized system implementable and effective. And in consideration of the resources of the renewable electricity in Japan, actually, we are at a very severe stage of securing all the possible renewable electricity to decarbonize our electricity first. So, in addition to that, how we can secure the extra renewable electricity to power the decentralized CO2 use system in the urban area, where the site is very restricted. That is actually the severe headache. So probably the decentralized system cannot be the entire solution for the carbon recycling in Japan. But as a technological sector, I would like to develop at least one option and let the society and the community to decide to optimize the entire system, probably partly incorporating such a decentralized system. And finally, talking about the cost benefit of the decentralized system, I think that if we just rely on the traditional thermal process, we have a rule of the reduction of the cost as for the expansion of the size. We basically employ either the membrane or the electrochemical system, which are new regime systems, which is not so much applicable to such a scaling rule of the cost reduction as for the size expansion. So probably, if we rely on such a membrane or electrochemical system, we may be able to make even a smaller scale sites, like the building scale CO2 capture and utilization process, still competitive to the large scale CO2 vacuum system. Thank you.
Okay, thank you. Right now we have the two discussion points. One is integrated process or separated process. That is the first one. And the second one is we should take another environmental impact or risk management or something. That is the two second discussion point. I would like to listen to the voice from the Norinaga-san and Noguchi-san. So please.
Okay, let me.
Hi, please.
Okay, thank you for your question. So first issues around the deck should be delocalized and separated, or intensive and concentrated methods. So in terms of the cost, and also to make the deck which can be competitive in the cost. So in a very conservative thinking or in a chemical engineering, so we need to make we need to use the scale merit, and then we reduce their cost to capture the carbon dioxide. So in that sense, so it is very important to make to realize DAC in a dense and very intensive method, so to reduce the cost, especially for the capital cost. In a distributed method, we need to make a numbering app, so to make a large scale. So that's why our approach is to utilize their liquefied natural gas coordinates, so which is limited. The position is we need to locate their deck systems close to their LNG terminal. So, but by utilizing such unused cold heat, so cold energy, so we can reduce their energy input when we regenerate their absorbent. So we can realize the deck, the temperature as low as possible, even at the ambient temperature, so we can minimize the energy input. So that's one of their advantage, what we think why we will do such a deck system in an intensive method. But the advantage of the deck is so we can capture their CO2 everywhere, so already in the atmosphere. So it is very important to think about their such an advantage, to utilize such advantages to do their carbon deck in a very distributed everywhere. Yes.
Okay.
Thank you very much.
Okay, thank you. Next is Noguchi-san, please.
Okay. Thank you very much for the very interesting question. The integration and separation. My answer is very simple. In my project, the answer is both is needed, because if we use the carbon dioxide, we have to produce the product.
In that case, the carbon dioxide is one resource. It's a raw material. And another resource is needed to produce a product. In that case, in our project, the concrete is another material, raw material. So because the concrete structure is anywhere, exists anywhere, and carbon dioxide is also anywhere in the atmosphere, we can combine together to make a new concrete. So the integration is localized in anywhere. So we need the energy to produce a new concrete, but the exhausted gas is also anywhere we can find. So currently, we are producing the concrete using the cement. It is localized. The cement plant is localized, and we can transport such cement. And also the aggregate is from the mountain, so that it's also localized. We can produce a concrete from such materials, and everywhere we are now constructing the structures. But in the future, that we can use such structures as a raw material and carbon dioxide in the atmosphere to produce a new concrete. The localized materials, localized plant will be established. So ubiquitous utilization can be the ideal state. Thank you very much.
Actually, cement factory is localized. However, that is not in the city, I think. So I would like to ask to the Kuni-san. Kuni-san, is there any project in the United States to take the CO2 from the air in the city? Do you have any project in such kind of that?
No, so yeah, I mean that's sort of to be determined. We have, as part of the infrastructure law that was passed almost a year ago, there is $3.5 billion to set up direct air capture hubs in the United States, at least 4 projects. Yeah, at this point, the locations of those are not known. They have not been determined as part of that process yet. But we are very much interested in sort of localized impacts and the potential for whether it's direct air capture systems or point source capture systems, whether or not there could be potential co-benefits that could affect the levels of criteria air pollutants in a certain region. So yeah, I would say it's very much of interest, but the projects that are the large-scale projects in the United States have not been chosen to have a particular location yet.
Okay, so Sik-san, do you have any opinion about duck in the city?
Yeah. I think there's quite a bit of interest of that nature, and there are emerging companies, there are startup companies in the United States that work on capture systems for buildings. As we had heard before also in a talk, that the concentration of CO2 is slightly higher in buildings in the city as long as we burn fossil fuels or hydrocarbon fuels in general. There's a somewhat localized increase in CO2, making that a little easier, still difficult and energy intensive. But certainly there are efforts that yet have to be evaluated, in my opinion. What is the smallest scale at which this makes sense? I think handling CO2 is somewhat benign, but if people are not careful, it can lead to accidents. As we know from old-style wine cellars or so, that you can suffocate. I think it's also not clear to me, in as much we can build capture systems that are essentially black boxes, right? Where the user has absolutely no contact with the sorbents. And many sorbents are toxic chemicals or are caustic, And I think that all factors in, but clearly people see benefits and business opportunities in very small scale DAC, and I think it will sort of be the typical startup excitement, and lots of ideas will be tried out, and I think this is really exciting to see, because these are small efforts and can be done with fairly limited effort. But what Kuni-san has described is very large installations, right? That require a lot of government support to install, to plan, to bring stakeholders together. And I think we need all of that, and therefore I think there's a lot of interest and activity that I see here in the United States in that sense.
Okay, yeah, thank you very much. So I would like to discuss about the methodology of the life cycle assessment. However, we have the other, two discussion point we discussed already. And I would like to have some question from the floor or online. Do you have any questions?
Inaba-sensei, before waiting for the question, I have a very short comment.
All right.
Yeah.
Pretty short. We have not so much time to discuss, so please.
So
Yeah.
As for the minimum size of the installation for the local CO2 capture, our team's assessment is that the one building, like 20 or 30 stair building, because we have a centralized air conditioning system there. So we have plenty of space to install our new system in replacement with the existing air conditioning system.
Okay, thank you very much. So in terms of the life cycle assessment, we need more information to carry out the life cycle assessment, not only the climate change. That is my point. Okay, thank you. And if floor has no question and online is no question, I would like to go on that, second part, that is the discussion part about the, CCU or CCS, okay? So first of all, I would like to, define the more, wording. That means, we know already CCS and CCU, that is carbon capture and sequestration, that is the storage, and CCU, carbon capture and utilization. But today we discussed DAC-U and DAC-S. That means, we have to capture CO2 from the air. That is a DAC, and DAC-S and DAC-U. And I would like to ask to the Kuni-san. Kuni-san said, Kuni-san said to us, you pointed out two items, two wording. One is removal, and second is avoided emission. So removal is DAC-S, and avoided emission is DAC-U. I can understand. So is that correct or not?
Yeah, no, I think that's the right way of thinking about it. And I think and Volker mentioned this earlier, I think we need both, right? Like I don't think we need to claim that one is more important than the other. But I do think that's a good way of thinking about avoidance and removal.
Okay, thank you. But avoided emission is just a comparison between the, is that a comparison? Just a comparison, I think. What do you think about that? That is not an exact removal, I think. Yeah, DAC-U is still important.
Yeah, certainly. Yeah, and I think to your point, the sort of the net benefit of that coupled system depends on a comparison, and the comparison to sort of the conventional way of making whatever that utilization product is. And so, yeah, and I think that's why LCA is such a great framework at helping to answer this question, because it sort of forces us to think about the function of a system, and when we do a comparative analysis to make sure it's a consistent analysis. So, yeah, yeah, absolutely. I think that DAC to utilization is potentially beneficial, and I think the magnitude which depends on the ultimate application of the CO2 and the conversion process.
Okay, thank you. Sik-san, you said track 1 and track 2, right? But in my understanding, track 1 is a DAC S and track 2 is a DAC U. Is that the correct understanding or not?
Yes, in your nomenclature, and maybe I can try to describe this in a slightly different way. I like to think about utilization, and ideally with CO2 from the air, that is DAC. And we cannot forget that there are many products that require carbon. And in that sense, we look at DAC-U as a process to provide these products. And in the process, we avoid CO2 emissions because we're not using carbon from fossil sources. So that overall is an environmentally beneficial process. But then I also need to say that there are these, what we call track 1 products, that still give us a product for everyday use, such as concrete or aggregates. And those permanently or durably remove the CO2 as well. So in function, they are like DAC S. But we produce a product, and that's why we call it DAC-U, which is very confusing. But I think we need to distinguish it based on those differences. And therefore, I think there's always some level of overlap between different methods. And I think when we use this track, I think it's easier to separate. But I also would like to think, I like the fact that today we are talking about direct air capture. Because as Kuni-san has shown in the nice overview scenarios, 4 different ways of capturing CO2, it gets really complicated if we do not start with CO2 from air. Right? Because then we do not achieve the optimum that utilization or storage could achieve in a climate sense. I think that has to be our first objective. That we do as much as we can to reduce carbon ballast in the atmosphere. While at the same time, of course, we have to meet society's needs for the products that we have.
Okay, thank you very much. In my understanding, track 1 is if we capture the CO2 from the air, track 1 we cannot use that is. We cannot use that one is a track 1, and if we can use that one, that is a track 2. That is my understanding. Is that okay?
No.
That is completely different?
And track 2 are utilization. So it's certainly
we can use.
Start with CO2 from air, and both use.
Okay.
But if you also look at one of your Moonshot projects that makes concrete, that concrete can durably remove CO2. And that's why that portion is doing the same job as storage. And I think the potential is huge. Just last week, we published a new report that shows that within less than 30 years, we could produce as much as 14–15% of all aggregates with CO2 carbonation. And depending on what we make, this could store up to 11 gigatons of CO2. So if we really are smart about this, we can lock away a lot of CO2 in products with a reduced need on storage, which is a societal burden because it costs a lot of money. Of course, it costs a lot of money to make these aggregates, but then we have the benefit of now having these rocks to build roads and houses.
Okay, thank you very much. So my last question is to all of you. That is the role of the private sector. I mean, Kuni-san said network of the to build up the DAC-U or DAC-S. However, I cannot see any private sector in your network. Is that true? Is there any private sector in your network or not? Yeah, your last presentation, last slide, you said the network of the DAC system, right?
Yeah, no, I mean, I think there are most definitely private sector elements that are required. I think to Volker's point earlier that sort of there's a huge continuum of scale that is necessary, and yeah, the DOE is funding things at lots of different scales. Starting at really early technology development levels, all the way up to larger scale demonstration projects. So, I think there's absolutely a need for the industrial sector and sort of private sector, and in fact, the U.S. tax code is incentivizing those actors as well through the 45Q credit, which provides a tax credit for utilization of captured carbon dioxide. So, I think it's absolutely critical, and I think it's necessary at all scales.
Okay, thank you. We have only 2 minutes. 2 minutes. So, Sik-san, what do you think about the role of the private sector for the DAC system?
Yeah, I think it's important, and if we look at who are the leading actors in commercializing direct air capture, these are all private companies that have managed to raise funds in a combination. Right? There's certainly, from a research point of view, there was federal funding in the beginning, but more and more they raise money from private sources. And I think this is really helping, because it brings a lot of attention, it brings a lot of focus, but also responsibilities to make sure that progress is being made, and the developers are held accountable for that progress. We have observed a manifold increase in private investment, venture capital funding over the last year compared to any time before in CO2 utilization. So I think we do notice that many believe that these technologies are now ready to be scaled. We see the Orca plant in Iceland. We see carbon engineering ramping up production, and global thermostat is the works too. And these two and Kleinworks in Switzerland, the pioneers, they have
we have only 30 seconds.
And now many more have sprung up.
Okay.
A lot of companies that are emerging right now.
Okay, thank you very much for your joining to our discussion. So I have only 30 seconds. Okay, thank you very much. I would like to give my great pleasure, thanks to all participants. Thank you very much. Okay, thank you. I would like to close this panel.
Thank you.
And also thank you very much for your interpretation. Thank you. Okay.
Thank you, Dr. Inaba and all the panelists. This is the end of the Moonshot R&D program.